Well, hello guys. I'm gonna make this video going over the 5.1 lesson in case you missed some of the class or you just didn't understand some of the stuff. Hopefully this video will help you. This is covering section 5.1 in our probability unit, our first lesson of unit 4. And in the notes handout, it's gonna be pages 1 through 8. Let's get started. So in this question, you are asked to try to figure out which likelihood is going to allow player 1 or 2 to be advantageous in this game. So your scenario is you pair up with somebody, roll a die. If either of you, if your highest number is a 4 or less, then player 1 wins. If the highest number is a 5 or 6, then player 2 wins. So you want to think about which is going to be more likely to occur, player 1 winning or player 2 winning. So make your best guess. I'm not going to tell you what it is. Just think about what you think it is based off the information here. But then what we're going to do is we're going to do a little simulation. So we're going to play this game. You can pick a partner. I'll play this game 20 times. You're going to record the winnings. And you're going to see in your trial who is going to be the victor. So I did a little simulation here, just using random dice generator. And well, let's think about when player 1 wins. Player 1's going to win when the numbers 1, 2, 3, or 4 are the highest. So look at my my dice over here, my pairs of dice, and you can see over here that in my scenario, 3, 4, 4, 4, 2, 2. 4, 1. The out of my 20 rolls, 10 of them gave me player 1 winning, which, so I guess in this case is kind of a tie, because in the other 10 rolls it's going to be 50% player 2 winning. So in my my simulation, they had equal chance of winning. Now you may have said player 1 was more likely to win because there's more outcomes. So you might think, well, I want to try this again, or I want to pool it with class data and see, collectively who's going to come out the winner most often. Now, what we did here were experimental probabilities. In other words, we did not actually calculate what the true theoretical probability is. We just, based off of our simulations, experiments, were able to figure out what this ended up being. And so in my one simulation, I'm looking at 50% player 1 winning. I don't know if that's close to the theoretical. So what we want to do is we want to think about, well, what is the what are the actual chances of getting a 1, 2, 3, or 4 on these 2 rolls, or 5 or 6? So what we want to do is we want to list a sample space. And you can see here, if you pause the video if you want to fill this table out yourself, you can see all the different scenarios, where player 1 roll is a 1, the other roll is a 2, 1 roll is a 1, the other roll is a 3, and you can see it filled out. So here is a filled out version of that sample space. And you might notice, well, there are 36 different unique possibilities here, because, well, there's 6 sides of the dice and there's 2 rolls. 6 times 6 is 36. This is what we consider a sample space. This is every possible outcome listed. So what do we do with that information? Well, if our goal is to figure out what's the probability of player 1 winning, we want to think about, well, in what scenarios in my sample space is player 1 going to be winning? And if you see over here, all the ones that have 4 or less as my highest number, well, that's 16, but there's 36 different possibilities. So it's really only 16 out of 36, which is 0.4 repeating, 44.4%. Now, remember, my simulation had 50%. Yours might have been higher or lower. But if we pulled our class data together, this is our theoretical probability. If we pulled our class data together, you'll notice that this experimental probability will approach the theoretical probability. And this is what we call the law of large numbers, which we'll define a little bit later. But basically is when you combine experimental results for lots and lots of many trials, you're going to get that closer to the theoretical probability. Another simulation we did in class was we tried to estimate the probability of me, or the likelihood of me making a free throw. And just to clarify, I don't play basketball. I'm terrible at it. So don't take any stock into what these numbers actually mean. But our goal is to use a simulator to figure out and estimate what my true free throw percentage is. So what we'll look at here is, let's see if I can pull up my app there. And we want to be able to record the, so I don't, this 80% is just, if you look at the free throw app here, it says the basketball team at State University claims that each of their players makes 80% of the free throws. Ignore that because that's not, this is randomly picking what my free throw percentage is. So I actually have no idea what it is currently here, but what we did in class was we kept shooting the ball, and you're going to see what happens. So after one shot, oh, I made the first shot. You can see 1 out of 100%. So we are we're hitting 1 for 1. So you could argue, well, my free throw percentage is 100%. But you're probably smart enough to figure out, well, you got to take lots of shots because you could have got lucky there, or we really don't know what the actual free throw percentage is because that's one shot. You got lucky, or if I missed it, you might have said, well, maybe you just we're unlucky the first shot, you need to warm up or whatever. So you got to take lots and lots of shots. So make sure that you record the percentage after each hit. I'm gonna shoot it again. And you can see here I missed the second shot. So now after 2 shots, I'm at 50%. So let's record that. 3 shots, looks like I missed again, 33%. 4 shots, see, oh man, look, I got lucky on the first shot apparently, because now I've only made 1, so I'm at 25%. Man, not doing so well here. All right, I'm at 20% now. I've made 1 out of my 5 shots. We're going to speed the process along and do 5 shots at a time. All right, so after 10 shots, I'm at 20%. 15 shots, I'm now at 27%, so I've gone up a little bit. After 20 shots, I'm now at 30%, doing better. All right, I bumped it up to 10 shots now. I'm at 30 shots here. I'm still at 30%. Okay, after 40 shots, I'm now hitting 35%. All right, you can see at 50 shots, I'm now at 38%. All right, after 60 shots, I've dipped down to 33%. Or you can see here at 70 shots, I'm now at 31%. And finally at 80 shots here, I'm at 35%. So if I were just to stop after 80 shots and I were to take a guess, what is my free throw percentage? I would guess, well, it's probably around 35%, give or take a few percentage points, right? So we're going to find out a little bit more on that later. So hopefully we've been keeping track of my percentages. You can see here, these are the percentages that I calculated from our simulator. The question is, what do you think my true free throw percentage is? Now, of course, if you were following along in class, it would have been different. But for this particular video, you might guess maybe it's around 35%, because that's where I ended after 80 shots. So the idea is we took a lot of shots to try to get somewhat close to what we perceive the actual probability is. So we could plot this on our graph over here, just looking at the percentages. You can see kind of models what we did on the website here. I included some of the intermediate points to kind of see that. And it ends up kind of leveling off in the mid 30s. And you're going to be asked the question, well, what can you do to make your guess more accurate? Well, of course it is. The answer is to take more shots. So speaking of more shots, I've run it for another 120 times just to see kind of where we're at. And you can see here, even after 200 shots, it's still around 35%. So let's show that true probability. And surprisingly, that true probability looks like it's at around 40%. So, our 200 shots clearly weren't enough to get our experimental probability to match the theoretical probability. So we would have needed to take probably several hundred more shots to really get that to creep up on there. So I'm just going to let that do another 1,000 shots, and we'll see what happens after a little while in the video. So let's go back and input our 40%. So we know that the true probability is around 40%. We're going to want to be asked to interpret that. So if my true probability is indeed 40%, then if I take many free throws, I will make about 40%. And that's what we consider the interpretation for this probability. So let's summarize a few things we learned in this little video. The probability, what is it? Well, it's the long run relative frequency percentage of an outcome occurring. It'll always be between 0 and 1. In the short term, it's very unpredictable. Like we saw, take one shot at 100%. That's obviously not a good indicator of what I could actually shoot. In the long term, though, it is predictable. Theoretical probability is what we expect to happen, while experimental probability is what actually happens. The law of large numbers is basically, if we do that chance observation many times, the proportion of times that outcome occurs approaches the true probability. In other words, it'll approach the theoretical probability. And we talk about something called the law of averages. Not a real thing. You're not due to get something just because you have a streak. That percentage is going to be the same. Like if you're flipping a coin, if you get 4 heads in a row, then the percent of getting heads in the next flip is still 50%. There's no memory of the prior flips for something like that. You have 3 criteria for a valid probability model. Criteria number 1, always make sure the possible outcomes are listed. Probabilities are always between 0 and 1, and they add to 1. Finally, talk about probability rules. This is kind of getting into the next lesson, but probability is always the number of ways something occurs over the total number of possible outcomes. We might be talking about complements, which is basically the not. The probability of something not happening. And we use this little notation here. You can see that little C there. That's the not, and we just subtract it from 1. You see mutually exclusive events, might be called disjoint, and those are things that cannot happen together simultaneously. So for general addition rule, the probability of something happening or this, like for instance, if I roll a die, probability of getting a 3 or 4, well, it's 1/6 plus 1/6 because you can get either one. So you're going to want to add those probabilities. And as far as interpretation goes, we always want to say, as far as probability, is what would happen if we did something many times. So in my example here, if I shot free throws many times, I would expect to get about 40% of them. And I ran this simulator up to 2,000 shots. And right now it's hovering at around 42%. And the only way I'm going to get that to be consistently around 40% is if I have lots and lots of shots. And I'm not going to wait around for that, but you get the idea. Many shots, going to get that true percentage to that experimental to be actually what it should be. This is some check your understanding questions. And the idea for these questions is you try them on your own first. So if you haven't done these yet, pause the video and see if you can answer these 4 questions. Then you can unpause it and you can see the explanation going through it. So take a minute to pause, and then you can go through these. All right, in this question here, we're talking about Skittles. So little fun-sized Skittle bags based on a very large sample. Here is the distribution of color. And you'll notice that, well, we're missing the red. So we want to know what we'll get that eventually, but explain what the probability of 0.214 for purple means in this setting. Well, it doesn't mean that I'm going to open a bag and I'm going to see 0.214% because it's a fun-sized Skittle bag, so you're not going to be able to calculate a percent like that. But over many bags opened, you would expect around 0.214% being 0.214 being purple. So if we randomly pick a Skittle many times from fun-sized bags, we expect the proportion of purple Skittles to be about 0.214. So as far as finding the probability for red, well, you have to understand these have to add to 1. So we have to add the remaining colors and then subtract that from 1. So you get something like this. Probability of red, there's your notation there, P parentheses. Add the other numbers, subtract from 1, and you get about 0.197. Part C, what's the probability that a randomly selected Skittle is green or purple? Or means to add. So you can add those two numbers together, green or purple, and then you get about 0.385. And then for part D, what's the probability not yellow? Well, everything but yellow is just 1 minus the remaining numbers, or you could add up the remaining numbers, however you want to do that. So basically do 1 minus 0.214, and that'll get you the remaining numbers. And that's the not yellow. And there's your notation for complements. All right, question 2, we want to talk about, based off of these probabilities here, which one would we want to use for the explanation? So a possible outcome, an outcome is impossible, that has a probability of 0. Outcome is certain, it's going to have a probability of 1. Again, try and get the other ones on your own and come up with an example, and you can unpause the video after that. So very unlikely is going to be 0.001, and almost the outcome will occur more often than that is not going to be 0.99, because that would be extremely likely, but having a probability higher than 50% is going to occur more often than not. So think about some examples that might occur. What kind of scenario is going to give you a probability of 0? Well, rolling a 7 on a die would be an example. And a 6-sided die, you only have 1 through 6. So how could you get certain? You could say rolling a 1, 2, 3, 4, 5, or 6 on a die. You're guaranteed to get one of those numbers, so the probability is going to be 1. For something very unlikely to occur, well, you could say 1 out of 1,000. If you had a random number generator and you randomly guessed the number and it gave you that number, you have a 0.001% chance of getting that. And the probability of 0.6, something like marbles. You could have 4 green marbles, 6 red marbles. Picking a red marble out of that bag is going to have a 60% outcome, so 6 out of 10. All right, in the game Wheel of Fortune, there is a 1/9 probability of winning bankrupt on giving it at any given spin. What's that interpretation? Well, it's not for one spin, but for many spins, you would say about 11.1% of the spins will be bankrupt. Question 4, in 9 consecutive spins of Wheel of Fortune, none of the spins lands on bankrupt. This next contestant worries that he is more likely to land on bankrupt now because bankrupt is due. Why is this thinking wrong? Well, the wheel has no memory. So the wheel is going to keep having that 11.1% probability of getting on bankrupt. So each spin has an 11.1% chance of getting on bankrupt, assuming it's spun correctly. The spin for the next contestant will also have an 11.1% probability of landing on bankrupt. There's no memory, and probability is unpredictable in the short term. Got a little typo there, so it's unpredictable in the short term. So thanks for this is a check for understanding for that first lesson here. The rest of the video is going to go over the next lesson. Actually, to make the videos a little bit shorter, I will make a separate video for the next lesson. Thanks for watching.